is a actually so first one, group forces addition. I think it should look like this. I separated these out. So yeah, I mean, like we've looked at how to add these 5 parallel forces and where the lines of actions are, and then we are also going to look at 1, 2, 3, 4, 5, 6. Bunch of random forces, and the posted PDF is actually a step-by-step explanation of how to do that, but I'm gonna cover that in the class. But the methodology that we use, I'll explain later, which that would be, so adding these forces would result in drawing something like this. And these curves are called funicular curves. And if you heard of the word funicular, which that means basically are either tension or compression only. And so if you think of a cable with series of weight hanging on it, that's a funicular structure because it's just a hanging cable, so everything is in tension. And if you think of the arches, which is the flip of that, that's also funicular structure, but it's compression only. So, but we are sort of like, but when we are adding these forces graphically, we are actually kind of learning a method to draw those funicular curves. So that's why I think if we had time, I would also go into explaining how to figure out the geometry of these hanging cables. So after I demonstrate the addition of the forces, this might run into next week now because we lost 20 minutes. But this is, so ignore this, but you can imagine a cable with series of weight hanging from it with given distances, and you can actually specify the maximum tension for any of these cables, and depending on that, it's going to determine how deep these cable can hang. So that's basically what we are going to do. So that's kind of the eventual goal of these 2 classes, which is actually, so the schedule wise, we have a class today on 19th. Is that a holiday, right? Some sort of a holiday. Yeah. So we don't have class on 19th, and then we'll have class in next Wednesday. So in two classes, I want to cover these funicular structures, which would prepare us to go on to the beam problems. I won't give you a homework today, but I think what it would be is most likely I will post a couple of videos that I would require you to watch before the class next Wednesday. So it's probably not going to be an hour long, but it's going to be a couple of videos to watch before the class Wednesday, so that that's your homework basically. All right, so far so good. So now if you have downloaded this file, so we are going to look at how to add basically these 5 forces, right? And it's pretty much what it's going to do, what the diagram is going to do is, if you imagine 5 weights falling, and if you connected them with a cable, it's going to drop down and draw like this sort of nice curved shape. So that's kind of what it's going to look like. But let's just refresh the methodology, right? So how to add all of these. And of course, I'm not giving it any units, but let's just say 1 inch equal 10 pounds or something. So let's say force scale 1 inch. Let's just say 1 inch equal 1 pound force. So we have a, right, so I mean you can get the lengths, but we have a 12 inch, so that's a 12 pound force, 9 pound force, 10 pounds, 15 pounds, 12 pounds, and at kind of a random distances, so 16 inches apart, 12 inches, 12 inches, 20 inches, right? Fair enough. So first thing to do is you want to add, or actually you want to pull these forces aside in order to connect them head to tail. So that's kind of addition of all of that. So luckily, because everything is in the same direction, it's obvious that whatever the result of addition, the magnitude of the resultant force would be 58-pound force. Right? If you're adding all of these 5 forces, then additional. So imagine you are pushing something like, imagine this is a plan view, right? And these 5 people are pushing a weird table that looks like this or something. And if that's a very weak force, so, but probably the table is lighter than that, so you are probably able to move the table. But anyway, so magnitude, magnitude of the resultant force. In this case, we know that because it's that's basically everything is in the same direction. That's going to be a different story if one of the forces facing the other way or something like that. But anyway, for now we know that's the resultant. And as a procedure, you want to, in order to identify this force on this diagram, we're going to use start point and end point. And on the left side, which is kind of showing the form of the thing, is, the first force is placed between this zone A and B. I guess I forgot to mention that I drew these lines of actions and labeled the areas between the lines of actions by alphabet. So the leftmost part would be A, so that's everything that's left to this line of action. Between these 2 lines of action, I named that B. Between these 2 is C. Between these 2 is D. Between these 2 is E, right? Yeah, the sound is working. That's good. Right. So it's probably easy to the easiest way to identify this force, now that we've named all these zones, we may probably refer to that force on the left side as AB. And once we pulled it to the side, the way to identify that is we're gonna call the start point of that force as A and the end point of the force as B. And let me just use the same color so that we have the correspondency. So in the same way that we can call this force on the left side as AB because it's lying between zone A and zone B, we can call this force on the right side as AB because it's starting from A and ending at B. By the way, we are going to call this diagram on the right, we're going to call that force diagram, because it's a diagram that's going to show the forces. And so similarly, the second force that we have is going to be called BC. So I'm going to, it already has point B as a start point, so I'm just going to put the end point, match the color just for clarity. So this force is BC here, which is the same as here, which is called BC here. And just to differentiate between, also oftentimes we refer to this diagram that's showing what's going on geometrically, we call that a form diagram. So just to differentiate between form diagram and force diagram, it's kind of conventional to use a uppercase for the force diagram and lowercase for the form diagram. Some books might have it opposite way, but it's helpful to differentiate the two. So basically just keep going with D, E, and F. So it should end at F, right? So I'm gonna just match the color just so that it's easier to read. Oops. So E would be this green and F would be this orange, right? So in order to determine the lines of action for the resultant force, in which case we know the resultant force as addition of all of that, so it's going to be a arrow that connects from A to F. So this would be our resultant, right? But it's actually placed on top of this, but I'm just going to pull this to the side just to show you, right? It goes from point A to point F, and the length of that guy is addition of everything, so it's 58 inches, representing 58 pound force. So I'm just gonna put this back on top of everything so that we know it's at the right location. Now, all right, so now how do we find the line of action for this resultant force? So obviously this is gonna be somewhere, right? And again, to remember, if you once you find the line of action, it could be anywhere along that line of action, but right now we don't know where the lines of actions are, so it could be it's somewhere here, but we don't know where it is yet. So yeah, so our agenda is to find the line of action for that resultant force. So I think some of you might remember, but the way to do it is super easy. All you do is you put a random point, and I'm going to call it P, and it can be actually anywhere. It could be here, you could put it here, you could put it actually like way over there, but it's going to be extremely hard to draw the diagram if you do that. So you want to be somewhere near these points. I'm just going to put it on the left side, but it actually works even if you put it on the right side. So now next thing to do is to connect point P with any of these guys. Sorry, all of these guys. So connect point P to point A, point B, point C, point D, point E, point F. And like I said, it doesn't really matter where you put it, right? But once you put it, it has to stay there. So I'll put it here. And so if you want to follow exactly what I do, you can place it at the same point. But if you want to be confirmed that it works anywhere, you can put it somewhere else. But anyway, another thing that's not necessary but it's helpful is to color these lines the same way as these alphabets, because once you have a bunch of lines, it's kind of harder to differentiate which one's which. It's match properties, so you can type in MAT and it should fill up. So if you say match properties, yeah. So basically I type in match properties and then it's going to ask you to select objects to modify. So I want to modify the line and enter, and then select source object. So I want to match it to this guy. And then you can actually pick what property to match, but I'm just gonna match everything. So keep doing that for all the colors. So everyone has this? Yeah. So now, I guess I'll wait. If you're ready, let me know. More or less something like this. Now we are going to construct a diagram on the left side, and it's fairly easy. I guess before we think about the meaning of that, we will just go ahead with the methodology. So basically what we need to do is, you see the correspondency between the line and the zone, right? So A is this guy that's connecting to the point A, and B is what's connecting to the point B, and you see also the color correlation. So what I do is basically all these lines should lie in the zone where it's marked with lines of actions. So what I would do is I'm going to copy this line PA into the zone where it's signified by alphabet A. These are the tricky ones because it's at the corner, but I will leave that for now. And then yeah, it doesn't really matter as long as you can see it. So let's just put it here. And it's actually kind of easier to deal with the edge ones later, but I'm just gonna start with A. And the next step is, if you want to copy B, you copy it to the B. But you realize that zone B is between these two lines. So you actually want to trim it so that that line only occupies the zone B, right? And you keep doing the same thing for the other ones. So basically you copy the C. Yeah.
So when you copy B and you said it only has to be within that zone, does it have to connect where the first line you?
Oh yeah, so
every
it's
single line has to connect.
Yeah, so this is going to do a weird thing later, but the principle is basically when you're copying it. For example, actually it's easier to explain it with C. So when I'm copying the C to the zone C, I have to make sure that it connects to the where I trimmed B, right? So again, I'm going to trim C so that it matches the zone C. So C is here, right, between these two lines. And so again, when I copy the line D to zone D, I will make sure that it's snapping to the endpoint of that C. So basically, make sure that all the lines are connected to the previous one. So if you follow the step, you should more or less, let me just make sure that it's snapping. All right. So if you follow this, oh, there's one on top of each other. Hold on, let me just make sure. P to here. So once you copied everything, it should, the angles might vary depending on how you drew it, but it should look something like that, more or less. Previously I drew it with a different point P, so it's gonna look like that, but it doesn't really matter. So anyway, so now we are kind of left with these two open ends, which doesn't really help for us. So it's actually these two when it doesn't have the end. So A is everything left to that, right? So and it's gonna keep going. So for these two end ones that doesn't have the boundary, we basically extend this back into. So basically, if you imagine scaling this line, you want to extend this so that it kind of like kicks back, right, from this line. You do the same thing to this guy. So you should basically get these two long lines that intersect somewhere in the middle. And that's actually what matters. So for the purple line, or the line PA, what's on the left side of this line, we can kind of ignore that, but sort of read it as, you know, I guess sort of like the reflection or something. But anyway, so A should kind of kick back into this zone, and same thing for F. You're gonna cut it. So instead of going towards infinity towards the left, it's gonna kick back. But still, all of these lines are parallel, right? So the line PF is parallel to this guy. The line PA is parallel to this guy. So now we have two lines kind of kicking back to each other. And what we need is the intersection point between these two. So that, you know, you want to have this kind of closed polygon with 1, 2, 3, 4, 5, 6 lines. And that intersection point that we just got is basically, that's what determines the line of action for the resultant force. So now we have this location so that we can anchor this resultant force, which is something that we added, you know, A, B, B, C, C, D, E, F. 58-inch line is, it can be dropped in here, and so basically along that line of action is where the resultant force is. So if you want to make sure that it's right, it should be somewhere like 13. So if you drew it, and if you want to measure it from the left line of action, it should be somewhere like 30.38102 inch or something like that. So far so good. Did you get it right, or yeah? Does that make sense? So actually I'm just kind of curious. So it shouldn't matter actually, even if you didn't get the same exact geometry, you should still get the same result.
Yeah.
Who got the right?
Like 30
points. Yeah. So you can get the.
As long as it's generally around that, that's correct.
If your tolerance is the same, it should actually be, unless I drew it wrong, it should be, or you should always get the same 30.32. That's slightly different. That's kind of annoying, but I might have snapped it wrong, or it might be actually like, let me see. This should be actually always the same. But you know, if it's around there, it should be correct, more or less. Yeah.
What if we got less than 30? If we got less than 30?
That sounds a little bit off. But make sure that everything is snapped, because sometimes.
It's
30 point.
It's 30.062.
You get everything.
Yeah,
I got
and then,
All right, but the idea is it's more or less always the same. So let me confirm whether it's like needs to be exactly. But you know, that's basically the method to find the resultant force, the lines of action of resultant force. I should get always the same though. Somehow, maybe. let me double check, but it should be around there. And just to demonstrate, if I drew it differently, so let's say I put the point P there. Should I change the background to black? Is it easier to see? Okay. So let me just demonstrate these. So let me just move this away. So same thing, the step is exactly the same, so B, C, D, E, oops, let's trim this, trim this, trim this. So it should be at the same. Yeah, so it should actually always be the same. So that means, I think, what I drew here, oftentimes what happens is like you think you're snapping to the point, and sometimes you're not. So I probably did that when I did this one. Or maybe I didn't snap to something right now. Oh yeah. So sorry, that's the mistake that I made, right? So it looks like it's snapping to that point, but it's not. So it's actually, all right. So yes. So actually, the precision of your drafting reflects on the precision of calculation. So actually, my answer was actually slightly off. So let me redo that so that it's correct. So I think, yeah, but it's gonna look almost exactly the same as this because it's just slightly off. So let me just quickly get back. B, C, D, E, F, and A. Should be 30.06. Oh shoot.
That's a lot closer to mine now.
Yeah. So I guess anyway, make sure that it's snapped somewhere. So what I do actually usually is because I'm lazy. It's kind of embarrassing, isn't it? But it's somewhere around there. I think I did it right. The 30.32. No? Okay, so let's say that's the right one. Yeah. So if you made a mistake with drafting, your calculation would be still off, a little bit off. But I think the beautiful thing about it is like it's still gonna be pretty close, right? So unless it's the exam. Right, if you know more or less, that's fine. Yeah, so make sure that it's snapping to the correct point. So yeah, that was a little bit embarrassing. But anyway, so that was for adding a bunch of parallel forces, and it's actually the same thing even if it's doing this, for example. So in this case, some of these are pointing up, some of these are pointing down. Do you have this too? Did I give you this? Oh no.
Yeah,
It's in there? Okay, cool. So let's say, let me just extend these lines of actions. So it's gonna be the same exact thing. So I'm gonna label it exactly the same. So A, B, C, D, E, F. The methodology would be the same. It's gonna look slightly confusing. So what you do is basically the same. It's a little bit hard to see, but what you do is basically you map this, right? And again, just for the sake of my laziness, I told you to use uppercase here, but I'm just gonna copy from the left side. So that's the first one is AB. The next one would be BC. So it's gonna have to start from B, right? And it's gonna end at point, sorry, let me copy this. So it's gonna start from B. So the second force is BC. So it's gonna start from point C, and then the end point of the arrow would be C. Let me make sure it's snapping, yeah. So it's on top of each other and it's a little bit hard to see, but that's A, so it's going up from A, going down to B, going back up to C. And the next force right here is CD. And because it's called CD, it should start from point C. And you know, this looks like another opportunity for a mistake, but the end point of that arrow should be point D. Same thing with this one between D and E. It should start from point D. Maybe I should have drawn these a little bit different size so that it's not so much on top of each other, but anyway, so this one upward arrow that we just copied, which is DE, also should end at point E. The last one, let's do this actually. So let me copy point F first, right? So this should start from point E, which is there, and it ends at point F. So your force diagram kind of looks like you starting from A, going down to B, going back up to C, down to D, and is that right? No, I did it wrong. No, actually going back to D, going back all the way to E, and going down to F. So it starts here and ends there, right? So that means, again, because everything is in same direction, your resultant is AF. So the magnitude of your resultant should be 10 inches, which is, I think we're saying that it's 10 pounds. Is that all right? Yeah. So now, the same exact process of placing a point P. And just because it's a little bit hard to see, let me have another view. So alright, so now the process is again the same exact thing. We're gonna place point P anywhere you want. I'm gonna put it, oh, you know why I made a mistake? Because I had a grid snap and it must have snapped to some grid. Anyway, so you're gonna copy from P to A, right? Next is P to B, P to C, P to D, P to E, then P to F. and the colors should match, so I'm gonna match the color to A, which is purple, B, which is blue, C, which is cyan, D, which is green, E, which is lighter green, and F is this orangish color. I'm just going to change these lines to where is it? Can change the line type to continuous so that you can see. So you see E, so A, B, C, D, and E. So you are not going to have that clean shape like you did before, but the process is exactly the same. So I'm going to copy. So I think starting from B was easier, so I'm going to copy the B to here. So B is that blue line. So I'll place that in zone B, which ends up being super short. So I'm going to extend it here. So B is this guy right here, the second from the bottom. C is the third one from the top, this light blue. Connect it to this guy, extend. D, where is D? D is this green guy. Going down, again extend. E is this light green, copy to right here, extend. So you get this kind of zigzag thing. And now we go back to this A, which is this purple. Instead of placing it outside, I'm gonna sort of reflect it back. Same thing with F, it's gonna kick back. And you connect, you can do a fillet with radius 0 with no join. It's gonna meet at that point, and that's gonna be your line of action. And the resultant is, as we calculated here, is this downward force going this way. And this can be actually, as long as it's along this line of action, it can be anywhere along here. But just to give you, I hope I did it right this time, but the distance from the left side should be something like 27.1 inches. If you want to check yours, well, I will check my previous answer, 27.1. Did you get it? No? This is a little bit graphically confusing to work with, but it's a little bit, but same exact process.
Okay, so you need this line to help.
It's a little bit quick. I mean, I'm gonna upload this video so you can watch it again, but how to get to this diagram was, yes, it was slightly cumbersome, but what you do is connect this one, right? I think the kind of fail-safe way to do is, because you know this will be called AB, what I'm gonna do is I'm gonna copy this to the side, right? And this is AB, so it's gonna start from A. It's gonna start end at B. next one, this one, is gonna be called BC. So I guess I'm gonna copy the endpoint first, right? Sorry. So I'll copy this, and I'm gonna add this at the endpoint. So the endpoint is now fixed, but this has to start from point B. So I'm gonna connect that to point B, right? Next one, I'll probably do the same thing. I'm gonna bring it to the side. I know the endpoint is D, right? I'm gonna drop it to start from point C, right? Next one is DE. I already know the start point, but it helps to copy the endpoint, and I'm just gonna move this to where it needs to start, which is D. And the last one, same thing. What? Copy. Last one should also end at D, so I will copy with the endpoint. I'm gonna move it so that it starts from E. So it should look like this. I mean, so if you read it from the top, it should be like E, A, C, F, B, D. Is that right? Yeah, E, A, C, F, B, D. So that's the first step, and then you connect the lines and shoot. Now we have 5 minutes. So I think this funicular thing, which is the hanging cable, I'm gonna do a video and then I'll have you watch it before the next class. But I do want to get to this one last one. So if you didn't get it right, you can watch the video. It's recorded, so don't worry too much. But I want to go to this last one, which is also covered in, so I think delete these. I posted this PDF called Group Force. That's excerpt from this. I don't know if you bought a book called Form and Forces. Which I think we have in the library too, but it's I bought the PDF version or electric version, and this thing comes with it. If you want to flip through the book, I think we have one copy at the library. You can look at it. You don't have to own it, because if I'm gonna use the material, I'm just gonna distribute it to you. But anyway, so it's kind of this like learning material that comes with the book, and it's actually showing what I'm gonna show you step by step in PDF in writing, so it might be even more helpful. But I drew the similar problem. If you on the right side of the file, it's not gonna be exactly the same because I didn't draw it exactly the same, but you get the idea. So now the difference from the previous one is that it's not parallel to each other, so it's slightly trickier, but not to be worried about, because the method is actually exactly the same. So we're gonna start the force diagram on the right side. Right, so the first one is right here, and A is at the beginning, B is at the end point. The next one, it's gonna start from B, it ends at C. right? And the next one, which is CD, which is this one, the third one, it's gonna also start from C, ends at D. Then the next one, which is between E and F, it's gonna start from E. Oh, did I miss something? Yeah, I missed DE. DE is right here. So I'm gonna copy to D, and the endpoint is gonna be E. The next one is EF. So it's gonna kind of kick back and goes to the F. And the last one is FG. And it's at G. So just following the logic of vector addition, we actually even know the direction and magnitude of the resultant force, which would be this. So your resultant force is AG, like that. But now we need to figure out the line of action on the left side, so that we can determine where this thing goes, whether it's here or there. So again, same exact process of picking a point P and connecting between P and A, B, C, D, E, F, and G, and it's again helpful to color code them. C, whoops, D is right here, E is right here, F is right here, and G is right there. So a little tricky thing is now the lines of actions intersect, so you want to choose the area where it's kind of spread apart from each other. And I think, I haven't confirmed this, but I'm actually pretty sure that it should not matter where actually you put it. So I will start from somewhere around here, but I think even if you start your diagram like somewhere around here, it should give you the same result. But anyway, just following the same procedure from the last time, I'm going to copy the PB line to zone B, which is roughly here. So let me say I'm going to put it right there. And probably even if you put it here or here, you probably get the same result. But I'm just going to put it here so that you can see better. I'm going to trim it with the action line of action of BC. I'm going to copy the line PC to lie on the zone C. I'm going to cut it with that line of action. And I'm going to again copy the D to zone D, which is right here. Again, I'm going to trim it. So keep following the same process. Copy the E here, and F is this right there. So I'm going to copy F to here, right? And now A and G should go back towards the middle and connect somewhere. So I'm going to do, no, A is right here, so I'm going to start A from there, and I'm going to use the G, which is the last one, to start from there. And you should be able to take the intersection point of these two diagonal lines. Come on. And that point right there determines the line of action for this resultant. So I'm going to place this here. But let's just do, because the line of action is here, so as long as this resultant is along this along this line of action, you still have the correct answer. So my guess is, or actually my conviction is that even if you drew your diagram at a different location, it's gonna have a slightly different shape, but your line of action ends up being here. But actually, how do I tell you? Well, it's kind of hard to tell you where exactly this line is. So, but if it looks like this, so it should be lying somewhere between here, intersecting this line somewhere there. But you should get a line like this. So if your result wildly looks different than this, then maybe it's a wrong answer. But again, you can follow the video. Also, the PDF shows the step. Where did it go? So same thing, it's doing the same thing, connecting resultant and the P point, and then doing this diagram. So it's somewhere here, right? I mean, mine and this PDF is not exactly the same because the geometry is slightly different, but anyway, so this was just kind of get you familiar with this idea of funicular curve and getting the resultant. So next week I want to talk about,
How did you choose the line of action?
for the last one.
Yeah, for like the line of action.
So we determined a point by intersecting this last line.
Right.
So that's the point to drop the line of action. And the line of action is parallel to the force. So if I just drew a really long line. I mean, I just took that resultant force and scaled it really big, matched property to this dashed line, and that's going to be, so basically that's your line of action there. So yeah, so in the next class, so I think I will post a video describing how to do something like this and maybe doing some explanation. And the last next week I want to talk about this tension only cable and compression only arch, and the understanding of that will relate to when we start analyzing the beam. You're gonna be drawing this thing called moment diagram, which is in the traditional method you'll be doing a lot of like algebraic calculation to get this diagram, but you can draw this using almost exactly the same process, and the understanding of what's happening in the beam isn't that much different from this hanging cable. Would be kind of an important intuitive understanding of that. So look forward to next week, I think. Yeah. So see you. Yeah.
Do you measure?
What did you measure that?
How did I measure which?
Like where it's placed?
Where this is?
Yeah, where if it's right or not.
So the point was identified by intersection of these two, right?
Yeah, but then where do you measure that?
Like you remember you did the measurement?
Yeah. So I mean, it's kind of hard to. So your point, depending on where you drew the diagram, it's going to be different, right? So yeah, so I think if it looks like this, you should be correct. Like,
That's fine. When that he needs to be able to.
Because I drew it down here.
So I heard yesterday was just a long, boring day.
Oh, you didn't go yesterday?
Yeah, I was sick. He told me, he's like, it's a good thing getting cold. I was like, why?
We did that fucking review from 1
Yeah.
5:30.
He told me, he's like, basically.
so I think one way to hold on. Let me stop the recording.